Right. So let's read this. This question is fuzzy. It's not very well worded questions. Okay. So therefore, you have extra pressure when you do this particular question. Right. So you know the idea behind memory address translation that we discussed last time. Okay. So this is your logical memory where your program look at it like that. This is your physical memory. That is your actual RAM. So this is bigger, this is smaller because reality is smaller. So how do you map? You have pages here, you have frames here. You have more pages, less frames. Okay, because the pages assume that the virtual memory is also part of it, but virtual memory is not reality. It's you need to copy it to the physical memory to use it. Okay, so therefore here you have the physical logical memory address. Here you have the physical memory address. So logical memory address has two parts. Physical memory address also has two parts. So this is the page number. This is the frame number. But this part is the same, that is offset. Which address of this particular page? Which address of this particular, which address of this particular page? Which address of this particular frame? So if it is the 10th address of the page, it is going to be the 10th address of the frame because page and frame sizes are the same. So therefore, this part is going to be the same. But this and this is going to be different. This is a wider one. This is a shorter one, right? Because you have less number of pages than frames than pages. How do you find this? Using the page table. So using page table, operating system maintains which page number is mapped to which frame. And the valid invalid bit says whether that number is valid. If the valid invalid number is not valid, so that page is in the virtual memory. It has to be taken to the physical memory, and then the new page number is added, and the valid invalid bit will be 1 again, not true. So now only you can do the page translation. Okay. So that is the concept behind memory address translation. Translating logical address. Sometimes we use the word virtual address also to physical address. Right. So now let's read the question. Okay. Assume that we have a computer that can use. Okay, let me copy this question. Because then we get more. Okay. Yeah. No. Let's use the same space. Okay. Now you have the idea. I explain you the idea again. So usually these questions are considered to be the hardest, one of the hardest by students, of course, right? Right. Assume that we have a computer that use 16-bit virtual address. Virtual address is another name for logical address. I told you sometimes the examiner use the word virtual address rather than logical address. It's a 16-bit address. So virtual things I will draw here. Physical things I will draw here. Okay. So virtual address, it is 16-bit. 16 bits width. Okay. Or the logical address. Assume that we have a computer that can use 16-bit virtual address from 0 to 64K. Now, this is the real confusing thing. So, it says 0 to 64K. Okay. So, that means the first address is 0. The last address is 64K. So, this is a little bit confusing. Let's assume it is 64 and K is 2 to the power 10. Okay, 2 to the power 10. So, because in computing, kilo means 2 to the power 10, no 1024. Because this is computing. This is not meters or grams or liters or milliliters. So, in other words, 64 is 2 to the power what? 2 into 2 is 4, 4 into 2 is 8, 16, 32, 64. 4, 8, 16, 32, 64. that is 2 to the power 1, 2, 3, 4, 5, 6. 2 to the power 10. So in that case, it is 2 to the power 16. So that means you have 2 to the power 16 addresses. Okay. Because it says addresses start from 0 to, right, 0, 1, 2, 3, up to 2 to the power 16 addresses are. That means we have, if you take entire logical memory or the virtual memory, of course, it has pages. Okay, it has pages, but altogether, there are 2 to the power 64 addresses. Sorry, 2 to the power 16 addresses. 2 to the power 16. So how did I get it 2 to the power 16? Because 64 into kilo, 2 to the power 10. 64 is 2 to the power 6. Kilo is 2 to the power 10. In integers, when the base is the same, you can add the integers, right? So that is your O-level maths. So 2 to the power 16 addresses are there. Okay, so this much of logical addresses are there. Right, so now let's keep reading. Assume further that this computer has only 32 kilobyte of physical memory. Okay, 32 kilobyte of physical memory. So when it comes to physical memory, now I'm drawing the physical memory. So these are the frames. So these are the pages and these are the frames. Remember the frame size is same as page size. Okay. It has 32 kilobyte physical memory, and that the page size, right? Remember here we have the pages, here we have the frames. Of course, the page size and frame size are the same. So therefore, page size or the frame size is 4 kilobyte. So that means so if you take this page, it's 4 kilobyte. Or if you take this one, its capacity is 4 kilobyte. 4 kilobyte. Okay. And full capacity is 32 kilobyte. Full capacity is 32 kilobyte. So that means how many frames are in the physical memory? 32 divided by 4. That is 8. That is a very simple, to make it simple, the examiner has make it very small. So usually your memory is not 32 kilobyte, right? Your memory is about 8 GB, 16 GB these days. But to make the computation simple, so the examiner has taken very simple, simplified values. So that means 32 kilobyte means every frame is 4 kilobyte. That means you have 8 pages. So altogether we have 8 pages or 8 frames, because 32 divided by 4. Okay. So if the question has not mentioned anything about the word size, that is how many each address is for how much of a data, you can assume that it is for 1 byte. Every byte has address, because the question has not mentioned. Actually, they should have mentioned it, saying that if every byte has address. But if the question has not mentioned anything like that, you can always assume that every byte has address. Okay, so that is something you need to make a note of that. Okay, so that means every byte has address. Okay, if not mentioned, otherwise they will say, okay, every 2 byte has address and so on. Okay, right. So let's read it. Now we have used this information. The above 16-bit address, so that is 16-bit address. Okay, so this is the address. Of course, the content is there. I just draw the address. So this is also the address. The content is there. Okay, each address has a content. So my assumption is here we have 16-bit address, then 1 byte of or 8-bit data here. Here also, it may not be 16-bit, it might be different, but 1 byte of data. Okay, so this is, if you have any questions, you need to ask. So this side, logical memory, it is address is 16-bit and data is 8-bit or 1 byte. If they have not mentioned, you can assume. Right, word size is 1 byte. So here still we don't know this width. This width, we want to calculate that, but we know that it is again 8-bit, right? Because if not mentioned, you can assume that every 1 byte has address. 1 byte of data has address. Okay, so this one still we don't know. So this is logical memory, this is physical memory. So usually your physical memory has less pages or frames than number of pages in the logical language. But let's see. The above 16-bit virtual address, right? 16-bit virtual address or logical address is made up of bits of the page number. Yes, page number. Right? Remember, so this address consists of page number and offset. And this logical address, so I just draw this part, okay? So this part is this page number and offset, okay? Page number and this one, that is physical address consists of frame number and offset. Frame number and offset. Frame number and offset. Offset is going to be the same. Offset is not going to be the different, but page number and frame number are going to be two different. Right. Now let's read. Above 16-bit virtual address is made up of bits of the page number followed by offset bits. Yes. How many bits in the address are required to store a page number in this computer? To represent page number, how many bits are needed? So first you need to calculate how many pages are there. Because if you have 2 pages, I need 1 bit. Remember? Because if you have 2 bit, I can call it 0 page, 1 page. So that is, if you have 4 pages, you need 2 bits. So first page you can say 0, 0 page, 0, 1 page, 1, 0 page, 1, 1 page. 4 pages, you need 2 bits. 8 pages, you need 3 bits. 0, 0, 0 to 1, 1, 1. Right? So therefore, if you have 2 to the power n pages, you need n bits to uniquely identify that page number using binary number. Right? So how many page numbers are there? How many pages are there? We have altogether 2 to the power 16 addresses. Right? 2 to the power 16 addresses. And each page can keep 4 kilobytes. Our assumption is one address can keep 1 byte. One address can keep 1 byte. So then we have 4 kilobyte of addresses. Sorry, 4 kilobyte of data. So that is 4 into kilo is 2 to the power 10 byte of data in a page. In a page. 4 into 2 to the power 10. So that is 1 page can keep this much. Okay, 4 kilobyte of data. So, but altogether we have 2 to the power 16 into, assumption is we have 1 byte of data, right? 1 byte of data. So that means altogether we have 2 to the power 16 byte of data. Right? 2 to the power 16 byte of data. And 1 page can keep 4 into 2 to the power 10 byte of data. Altogether 2 into 16 byte of data, because 2 into 16 byte addresses, each address can keep 1 byte. But 1 page can keep 4 kilobyte, 4 into 2 to the power 10 byte. So then only byte to byte get cancelled. So then we get number of pages. What is the number of pages? So 2 to the power 16 divided by 4 is 2 to the power 2. 2 to the power 2 into 2 to the power 10 is 2 to the power 12. So when you divide, this is 12. So when you divide, remember 10 plus 2, 4 is 2 to the power 2, 10 plus 2 is 12. When you divide, you can subtract the integers. 16 minus 12 is 4. So therefore, you have 2 to the power 4 number of addresses in a page. Right? 2 to the power 4. That is 16 address. Sorry, not addresses. You have 2 to the power 4 number of pages. Because this is total capacity divided by capacity of 1 page. So that means you have 2 to the power 4 pages. 2 to the power 4 pages means 16 pages, right? 2 into 2 into 2 into 2. 2 into 2 is 4. 4 into 2 is 8. 8 into 2 is 16. So we have 16 pages. So if you have 16 pages or 2 to the power 4 pages, how many bits we need? 4 bits. Right? 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, and so on, 0, 0, 1, 1, and up to 1, 1, 1, 1. So if you need 16 different numbers, binary numbers, you need 4 bits. 2 to the power 4 addresses means you need 4 bits. So therefore, the width of the page number part must be 4 bits. 4 bits. So let's double check the answer. Right. How many bits are required to store the page number in this computer? 4 bits. So in the marking scheme, they have not given the steps how to calculate it, but that is how you get it. So there's no magic ways. So you must use all your logical thinking. So that is one of the toughest question in A-level ICT papers. But you can get the same type of question. Of course, the next year also they had a similar question. So any questions? So if when you're going for the exams, right, so you must face the reality, right? I don't want to keep you in a fantasy world and say that, okay, you guys are now ready for the exam. So you must, this is your reality. This is your A-level ICT exam papers. This is about 4 years ago. Now the exams are getting tougher and tougher and tougher and tougher each and day and day and day. Maybe this is a Corona period. So they make it a little bit easier. I think maybe just before the COVID time. Right. So that is how you get. So the page number part needs answer is you need how many bits? 4 bits. So the answer is you need 4 bits. 4 bits. But you need to get that answer first, right? You can't just say 4 bits. Right. So any questions on that? Right. So then the second part, if you don't have any questions, so you must know that the page size is same as frame size. So there's something called logical address or virtual address and physical address. And if you have 2 to the power n pages, you need 2 to the power n pages, you need n bits for the page number. So we just calculated how many pages are there because they have given you the total number of addresses and what is the size of one page. And you must always have that assumption. If they have not mentioned, each byte has address. So that is why when they say 4 kilobyte, we assume that there are each byte has address. Each byte has address, and altogether we have 2 to the power 16 addresses. Like altogether 2 to the power 16 addresses. One page has this number of addresses. So therefore, how many pages? This divided by this. And if when you get 2 to the power 4 pages, you need 4 bits to uniquely identify a page in binary level, because that is the first part of your logical address. Okay. Right now you know that page number need 4 bits. 4 bits. And now, of course, we can calculate the offset as well. Right? How many bits we need for offset? Because each page has 4 kilobyte of data. So 4 kilobyte means 4 into 2 to the power 10 data, byte of data. So that is 2 to the power 12 byte of data. So each page has 2 to the power 12 byte of data. And if you assume that each byte has address, so you have 2 to the power 12 byte of data, right? So each byte has address means you need 12 bits to uniquely identify offset. 12 bits because it's 4 kilobyte. So you need 12 bits for the offset. And if this is 12 bits, this is also 12 bits. So here physical address also has this offset part 12 bits. Okay. So offset is going to be 12 bits. Because this is 12 bits. Now we have fully calculated this part. But we don't know still how many bits are required for the frame number. Okay, frame number. That also, if you actually now we have the information for that also, because physical side it is 32 kilobyte and each page can have 4 kilobyte. So therefore, how many this is how many pages, how many frames we have? 32 kilobyte, 32 into 2 to the power 10 divided by one page, because the frame size and page size are the same. 4 into 2 to the power 10 is the frame size. So 2 to the power 10 get cancelled. 32 divided by 4, 8. Right? 8. So you have 8 frames. Right? You have 8 frames. We had 16 pages, 2 to the power 4, but we need only 8 frames. Right? 8 frames. So 8 frames means 2 to the power 3 frames. That means, so this part is only 3 bits. Because in order to represent 8, because this is your page number, sorry, frame number. In order to identify 8 pages, 8 different pages, sorry, 8 different frames, you need 3 bits. That is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. 8. To represent 8 addresses or page frame numbers, you need 3 bits. Now we know that this is 4 bit and 12 bits. This is 3 bits and 12 bits. Okay. You can already see that, remember the frame number is 3 bit. You can see it's 3 bit. It's 3 bit. And page number they have given in decimal, but obviously it must be 4 bits. It must be 4 bit because we have 16 pages. 16 pages. Okay. But 8 frames. 16 pages, 8 frames. So therefore, you need one more bit for the page number. Right. Now let's read. User runs a particular program having size of 32 kilobyte on this computer. So 32 kilobyte is again the same thing. Okay. Same thing, 32 kilobyte. So that is logical address. So logical address, it sees it as 32 kilobyte. A few selected field for the page table of that process at a particular time are shown in the figure below. So this is the page number mapped to the frame number, okay? But if the present absent bit is 0, that is invalid. So that is why the frame number is 0. Frame number is 0 means it's actually not in the physical memory. It is in your secondary storage, hard disk. So then it has to take that frame from virtual memory to the physical memory, and this must be updated, and then it will be 1, and then only you do the translations. For example, if the page number is 2, you are not in a position to do the memory address translation. But if the page number is 3, yes, I can say what is your physical address. Okay. Right. So it says frame number is indicated in binary. Yes, we can see that it's indicated in binary. Virtual addresses, or virtual address means logical address. On page 0 are from 0 to 4095. So that is page 0. Then page 1 are 4096 to 8191 and so on. Okay. So that means how many virtual addresses are in one page? One page. Because the first page, page 1, this is page 2. This is a really tough question, right? Really tough question, but you have no other option, right? Face the reality. So first page, this is a logical side. Okay. That is why they talk about pages. 0 to 4095. Then that is page 0 or the 0th page. First page 4096 to 8191 and so on. Okay. So that means how many addresses are there in a page? 4096. 2 to the power 10 is 1024. 1024 into 2 is 2048. That is 2 to the power 11. 2048 into 2 is 16, 1, 9, 4096. So that is 2 to the power 12. Okay, 2 to the power 12. So that means you have, it looks like you have 2 to the power 12 addresses in one page. 2 to the power 12. Okay. So that is correct, right? Because we have the offset as 12. So offset 12 means we have 2 to the power 12 entries. So that is correct. Or we have already calculated, but this is just additionally they have given. Actually, we don't need that. We have already found that there you need 12 bits for offset because there are 2 to the power 12 entries in a page. Right? 2 to the power 12 entries in a page. Anyway, that is they have given it in another way also. If you miss it in the previous approach. Right. So therefore, now you know that your logical address, again, it confirms that your logical address has two portions, that is page number 12 bits, and of course your page number 4 bits, page number 4 bits, and offset 12 bits. 12 bits. Right. So that is again confirmed that our calculation is correct. The present absent bit indicate the validity of the entry. Okay, that we know. So if it is 1, valid. If it is 0, it's not valid. Okay, because it's in the virtual memory. If it is 0, then the relevant virtual page is not in the physical memory. Okay, so that we learn. Assume that in the above process, the virtual address is this. Right, so this is my virtual address or logical address. Remember, it has 4 and 12. So this is your page number. This is the offset. Okay, so this is what we want. Okay. The above virtual address is mapped to physical address this. Okay, you can see this part is the same because offset is not going to be same. Offset is going to be the same, but it has a different frame number. So this is the page number and this is the frame number. Right? This part is not going to be different because offset is offset because page size and frame size are the same. So page fit into the frame. Right. So explain it. Now you need to explain it. Why is it like that? Why is it like that? So you have to explain, you need to explain that. So this, you can just separate it first. Say this is the page number, this is the offset. You can again write it and just write it. And this is the frame number and this is the offset. And you can say that the offset is the same because page size and frame size are the same. And from the table, this page number 0011 is because the page number is given in decimal here. So, but of course, in the address, it is binary. But because your page table, it is mentioned in decimal, you need to convert this into decimal. So when you convert this into decimal, this is 3. 0011 is 2, 2 plus 1. So therefore, you need to highlight this 3. So their page number is 3 and it's valid because 1 and its corresponding frame number is according to the page table 110. So you can see it's 110. You need to explain that. So the page number is 3. In the page table, page number 3 is a valid page and it is mapped to the frame number 110. So therefore, your physical address has 110 this, and you can even mention that this offset part is not changed. So therefore, offset has the same value, but 0011 has changed to 110. So you need to write that. Right? You need to write that. in this space. Maybe you can draw like this again, right? You can highlight this in the paper, because you can highlight that, because someone who mark can see that you have highlighted that. Or you can just draw something like this and something like this. So somehow you need to explain that, yes, I know what happened, and write simple explanation. But you need to do these calculations as well. That of course you did for the previous question. Okay, so therefore answer is, that is how you get this physical address, or sorry, logical or virtual address map into this physical address. Okay, next. So any questions? So let's look at the marking scheme answer. Entry 304, sorry, not this. Write down the value. Which one is that? 4 C part 2, right? Yeah, C part 2. Right, you can see, refers to the page number 3, right? Refers to the page, that is, they are referring to this page number 3, and offset this. It is mapped to frame number 110 from the table. So therefore, it is 110, and the offset is just copied. Just copied. So therefore, the virtual address is this. Of course, this is very short answer. So you should be able to explain it much better than this, because you have enough space. Much better than this. So, okay. Of course, in the marking scheme, they try to use the shortest possible answer. But because this is the essential, you need to have it to get that mark. Right? Get that mark. So make sure you get that mark. You never risk losing a mark. Okay. Right. Any questions? So I gave you 1 week for you to think about it. I know if you were not able to do it during last week, so don't worry. This is one of the toughest question in history of A level. Okay. But once you do that kind of a question, you must have that courage, right? In the future, if you get this kind of a question. But I know this is very tough question. But if you know the subject, if you understood the subject, of course, you can tackle this kind of complexity. And you can't skip these questions, right? So these structured paper questions, you can't skip. You get 3 questions, you need to answer all 3. Okay. So answer all the questions. Okay. Part A. You can't say that, okay, this question is tough, I will do the other one. Of course, the part B you can select. Okay. You can select 4 out of 6. But here you get 3 questions, you must answer all 3. Right. So let's move on to our next question. The last part of the question. Assume that there was a request for the virtual address. Virtual address is another name for logical address, right? You know that this is the page number and this is the offset. Due to set of tasks that the operating system initiated to fulfill that request, the present absent bit of the page number 6 in the above page table change. Right? So the operating system got a request from a software or the running programs to translate this virtual address or logical address to the physical address. So while operating system is doing that, the question says the present absent bit of the page number 6 change. Right? Present absent bit of the page number 6 change. So page number 6 is this one. So this one. So you can see that the present absent bit is 1. Maybe it has changed to 0. Because change means it has changed to 0. Right? Right. So let's read the question. What is the likely 15-bit physical address that the virtual address will be mapped to? What is the likely 15-bit physical address this particular virtual address, that is the same address, is mapped to? So that means you can see that, so this address 0001. Okay, 0001 is the page number. So that means the page number 1. So this is page number 1. So, okay. So then what is the page, the frame number that page number 1 is mapped to? So page number 1 is mapped to 000, but it says present absent bit is 0. That means actually there's no corresponding valid frame for this page. So that means that particular frame is in the virtual memory. So that is why present absent bit is 0. So why is it present absent bit is 0? So the corresponding frame for this page is not in the physical memory. It's not in the RAM. It is in your extended RAM or your secondary storage or virtual memory. So that is why present absent bit is 0 and the frame number says dummy value says 000. So therefore the question is when that memory address translation initiated, all of a sudden, so this one has changed from 1 to 0. What can be the possible reason? Anyone? Use your common sense, logical thinking, the theory you learned last week. You can clearly see that you try to find a particular page which is not in the memory. So therefore, in order to take that page to the memory, right, you may need to take some other page to the virtual memory. So, because you need to find some space in the memory. So therefore, most probably, this particular page, which is corresponding to this frame number, has been taken to the virtual memory so that that memory can be used for to upload or take the frame corresponding to this page to the memory, so that then we have a valid physical memory address. So most probably this particular frame is now in the virtual memory, and this may have changed to 111, and this is changed to 1, because this frame number is now used by this particular page, because this is put it into the hard disk and corresponding frame is now taken to the memory. So that is why, because this changed from 1 to 0, I can assume that now this has changed to 111. So this happens first, then happens this, then this become 1. So that is one possibility. Right? One possibility. So that is what the question says. What is the possibility? So then the question is, what is the likely 50? That is why they say likely, because we are not very sure. Because of this change, maybe this is what happens. So then what is the physical address? So this 0001 may have changed to this one's page number, which is 111. So therefore, likely physical address is 111, because that is the one we may think that this is, because this changed to 0, maybe we are using this particular frame now. And of course, the offset doesn't change. So therefore, this is not changed. Therefore, this is the likely physical address for this particular logical address after those things happen. Okay, after those things happen. 111, 4 zeros, 4 zeros, 4 zeros. Let's double check the answer. Yes, 111, 4 zeros, 4 zeros, 4 zeros. Right, that's it. So you can see it's not an easy question. But if you know your subject, that is not a hard question also. But for average person or below average person, this is near impossible question. If you just rely on your memory without understanding. So that is why I'm always saying, understand the concept. Yes, it's difficult, it's tough, it's challenging, but you must face the challenge, face the reality. Right. So now you must be able to do the any questions you're having? So that is 2020 paper. Now there's a similar question in 2021. Sorry, 2019. Make sure you do the 2019 question 4. A, which is related to file handling. Okay. And B, which is related to, again, this is related to process handling. This is related to file handling. And this is related to memory handling. So you must be able to do A, B, C, all three. Okay. All three. Similar question. Similar question. So we will discuss this question, but now I expect that you do this question. I was not expecting for you to do this question because you have not done such a question. But now with this experience, right, do your best without looking at the marking scheme. Do this question by yourself, especially the C part, because the other parts are pretty much opposite. Other parts also you must do. So we will do this question and then continue with your network subject topic in the next class. Okay, right. So we stop at this point, right? Thank you.